it's faster. So we're going to be using that. In particular, we're going to be using it to evaluate derivatives of the dynamics and do numerical optimization. Have a bunch of models that we can import from URDF. Our approach to control, we have lots of approaches to control. The main one is something called model predictive control. I'm sure you all know the idea. Basically, you're in some state, you plan an optimal trajectory for some time into the future, you start executing it. The world deviates from the plan because the world is evil, but that's okay because 10 or 20 milliseconds later you replan, and then you're very reactive. Can we play the movie, please? So I'm just going to show you that idea in action. This is a very simple thing we did 2 years ago. So controller knows two things. One is physics. The other one is that it has to hit the ball in whatever way is necessary to send it back to the paddle. It's completely reactive. You can push it around. You can grab the ball, and throw another ball. Keep going. Of course, people have done things like that in the past, but they were very specialized solutions. This is completely changed. So now we're going to use exactly the same algorithm to do other things, now in simulation. These are contact forces. This is a 60-bit with a mouse that you can use to put forces into a simulator. The blue thing is what the controller is thinking. So the blue thing is the plan. And for example, you see it knows it's going to fall, but it also knows how to get up. It doesn't have any control strategy that's being pre-computed, let alone hack. This emerges completely in real time. It can invent all kinds of things like somersaults and stabilizing strategies. This is really important. So we're going to introduce a huge model here. We make the mass 2 times smaller. The controller has no idea we changed the mass. So it's working with a computer-owned model, and yet it kind of works. This is what happens if you gain a lot of weight while you're sleeping and try to get out of bed. And your brain hasn't calibrated yet. It's difficult, so don't do it too much. Okay. Same idea applied to a full humanoid. The task is to get up. So the cost function just says, put your torso 1 meter over your feet. We don't care how you do it. This is passive dynamics. The red things are external forces we put into the simulator so we can drag it around. When it's orange, it means that we enable the controller and it invents how to get up. Once you get the Boston Dynamics robot, this is the first thing we're going to do to it. If it breaks, we're going to quit and we're going to join Stefan Schall's team because their robot never breaks. So you can see that you can basically do whatever you want to it and it's going to figure it out. This is the only simulation I'm showing you that runs slightly slower than real time on a single desktop, but if you multiply it on more processors, you can go. And then the last thing I will show you is a little quadruped that's happily walking down. So of course, like here we're basically inventing control as we go. There's no reason to do that completely. We can have whatever offline policy we learn, but anything we do, we're going to put NPC on top of it and hopefully stay.
From aerospace engineering at the University of Kansas, and I'm collaborating with Dr. Do Kim right there from Korean Institute of Science and Science and Technology. So I may have underestimated how long 5 minutes are, so I just have introduction slides. I don't have any fancy things, so don't expect anything like that. And so this is our team. Obviously, we're in Track B, and at KU, we're going to deal with high-level cognition and autonomous mission command, and we'll also implement supervisor intervention for Kubernetes. So what's important to note is that instead of starting with teleoperation and trying to move it toward autonomy, what we're trying to do is, as crazy as it sounds, we're trying to start with fully autonomous system and trying to inject some human intervention as needed. And for that, we need some expertise in robotics, obviously. So my folks at Korean Institute of Science and Technology, KIST, they will do mid to low-level control and simulation and hardware management and integration of entire control systems. If you might say that they're doing all the job, but we're trying to do some more high-level stuff on it. Okay, so this is how we plan to organize our system. So you can see that human supervisor have access to all the levels of the system. So at the top we have ICARUS, a cognitive architecture I've been working on. So it gives you cognitive abilities. And we have IHC for humanoid motion control from KIST. And then we have ROS-based sensors and perception and those kind of stuff. And then, of course, we have VFE platform. And this is how the architecture looks like. So basically, it goes to cycles, just like us. And it proceeds from the environment, and it makes inference on top of those, and makes decisions to what it needs to pursue at a given time and what it needs to do at a given time. Okay. So that's the cognition part of it. And we have motion control architecture called IHC. And this is a very modular system, and it has input-output components. You can plug in simulation engines or the hardware, and you can easily switch back and forth. And we can have different motion generation modules plugged in. And one good thing about this approach is that multiple people can work on the same system at the same time. So hopefully we'll be able to do all this stuff and finish it on time and be successful for the competition. And as I said, we're University of Kansas team, and we are close collaboration between KU and your Institute of Science and Technology. Thank you very much.
Okay, so the previous speaker wasn't sure if we had enough slides for 5 minutes. When I got the email requesting slides, they said no more than 2 slides. So either I can't read or nobody else can count. So I have 2 slides. My name is Rob Burridge. I'm from Track Labs, a small company in Houston. Track Labs was formed over 15 years ago, 15 and a half years ago, by a group of people that were doing research for Johnson Space Center in robotics and artificial intelligence. Of the 10 people who were doing research 15 years ago, 7 of us are still at the same company. So that's pretty unusual for a small company. During the past 15 years, we've had a lot of experience with many different robots. At JSC, Robonaut, one of the original founders of Track Labs, was named Rob Ambrose. Some of you guys have probably heard of him. He started the Robonaut project, and of course that's been very, very successful at JSC. We've also had experience with the AirCam ground demo, Centaur, which was really a 4-wheel base with Robonaut on it, both the Centaur 1 and then more recently the Centaur 2. You can saw a picture of that from Nick's presentation. What we see down here, I think hopefully everybody can see it. We see Robonaut autonomously finding a lug nut driver, basically a drill, and tightening 4 lug nuts completely autonomously. In the next set of 4, those are snapshots from videos. The videos are on YouTube. Robonaut is on a Segway following a person and responding to commands by handing that, actually receiving a wrench from that person. The person said, take this wrench, and Robonaut held out his hand with vision, found the wrench, and took it. The third one there is work I did in collaboration with Rob Platt and some others, where Centaur 1 found the back of another vehicle, drove up autonomously, recovered a box from the back of it using a 2-armed grab, and drove away with it. And then the 4th one there was a peer-to-peer project that we did in collaboration with Ames Research Center in California, where Robonaut was a part of a multi-human and robot collaborative team, peer-to-peer project.
Okay, so Track Labs, we have experience in robotics of various sorts, especially 3D perception and especially architectures, robot control architectures. Our approach generally is to stuff as much autonomy in there as we can, and then provide the ability to pull back on that, essentially slide the amount of autonomy back and provide operators more access to controlling at different levels. One of the things that I've been doing a lot lately in the past, say, 4 or 5 years has been this system that we call Piggy, which is one of these. Sorry, what did I do? Sorry? There we go. Okay. So this is our general architecture. On the upper left there, that's a snapshot from some collaborative work we were doing with AIMS and JPL, predictive interactive graphical interface, which we call Piggy. The operator interfaces across a time delay, where we actually use predictive models to predict the actions of the robot in response to the commands that have been sent. So the commands tend to be high level, right? You don't really want to be doing that with a stream of commands, of continuous commands, but if they're discrete commands, you can tend to predict the action pretty well. We have a lot of expertise in 3D object perception, going back to the days when stereo vision was a challenge, and more recently using a lot of laser LiDAR. Down in the lower right-hand side there is a picture from my thesis work 15, 18 years ago, doing dynamical juggling with Professor Kodacek. Rob Platt has a lot of experience with two-arm manipulation, and I think he worked on the Robonaut 2 projects, and more recently has gone to MIT and is now at SUNY Buffalo. And really collaborated with Rob in this project. I think my time is just about up. So,
My name is David Conner, and I'm a senior research scientist with Torque Robotics, and I'm here to introduce you to Team Vigor and our approach to collaborative autonomy. Our focus is really on this, addressing the issue of how do we make the best use of a human in this human-robot team. And so we're going to have a multi-view OCU that have intuitive interfaces that allows the operator to augment the world and really immerse the operator in the to get the robot's eye view. But then on the flip side, we're going to look to have sort of a more operator-centric focus so that it's very easy for the operator to choose multiple actions so that they can control the robot. Now, next slide. So we're going to sort of focus more on what our team background is. And so I'm with Torque Robotics. We were the software lead for the third place DARPA Urban Challenge team, Team Victor Tango, but we were sort of uniquely positioned as a company to actually be able to transition this technology, to commercialize this technology. And so taking that, adding on to our ongoing research and development in perception, autonomy, motion planning, and even doing some work in prediction, we've developed what we call our robotics building blocks product line. So we have drive-by-wire conversions, safety systems. If you need a platform-independent safe stop, go to our website, we'll sell you one. We also do perception and autonomy work that you can buy and integrate yourself, or we provide complete solutions to customers in agricultural, academia, the military, and some work in mining. And our core philosophy is this just continual design, build, test philosophy, where we focus on getting the systems out into the real world, testing in realistic situations, and also testing with the end user in mind. So I'm going to let my colleague from Virginia Tech tell you a little bit about his group.
Hello, I'm Felipe Passin. I'm from Virginia Tech. I'm advised by Dr. Beck. We're part of the Center for HCI, where we focus. Yes. Can you move to the next slide, please? Where we focus on the human side of computers. Our expertise lies in 3D user interaction, where we look at physical interfaces, 3D gestural interaction in space, We have a lot of experience in competitions too, where we placed first in 3 of the last challenges, the 3DUI challenges from the IEEE 3DUI conference. And we look at this problem as a user interface design problem, where we need to design the interface to communicate to the user what the robot state is, what the sensors capture from the environment, and also how to communicate with the robot effectively. So now I'm going to pass the ball to Oscar.
Next slide, please. My name is Oskar von Strick. I'm from TU Darmstadt in Germany. So we add to the team a great pool of talents and expertise, which is all competition proven, like the other team members, in our case in RoboCup competitions. So we have search and rescue robotics, we have humanoid robotics, we also have expertise in dynamic robot modeling, simulation, optimization and control, but also in behavior modeling, behavior testing. As robotics for humanitarian assistance and disaster relief is a very tough challenge, but it has not received so much attention and also not so much funding in the past. So we plan to make as much as possible of our developments open source after the project. So I would like to conclude that may the force with us all while we jointly tackle this bold challenge, but please be aware the talk is leading team vigor. Thank you.
Hi everyone, my name is ICARUS. I am the project lead for the RE Squared team. RE Squared is based out of Pittsburgh. So with our friends here from the two teams we're trying to get on, I think Pittsburgh is well represented. We're the prime contractor, and our role will be basically the system integration. We also bring a lot of technologies related to manipulation to the table. Also on the team is the University of Texas at Arlington Research Institute. The project lead on that is Professor Dan Poco, who's in the audience today. And they bring a great wealth of information and knowledge on perception and controls, particularly controls of high degree of freedom systems. And finally, rounding out the team, we have SOAR Technology out of Ann Arbor, Michigan. They're a small company that specializes in AI and user interfaces. And so they're going to be providing the human-robot interface, which is based on their SOAR cognitive architecture. The next slide, please. And one more click. So what I wanted to do was just share with you some of the guiding principles of our approach. You know, we really don't have a particular software architecture or technology that we are building upon. Essentially, our plan is to take advantage of the technologies available from University of Texas and RE Squared, but also what's out there already. I believe the true innovation is going to be the integration of these technologies and, of course, the application of them to the real world, which, as we all know, can be very tricky, or, in this case, the simulated real world. Next slide, please. Basically, we're planning to return any project-developed software back to the greater community. We think that this is an important outcome of this project. We've seen this idea in some of the other team slides, but we believe that we're going to need a sliding scale of autonomy, where certainly we want the robot to perform the task as autonomous as possible, but if needed, to fail gracefully back into teleoperation, and by this I mean more interaction with the operator. And finally, we recognize that it's going to require a pretty powerful human-robot interface that's predictable, reliable, and informative, which is why we went with SOAR Tech. With their technology, you can have more of a dialogue with the robot, where you can understand what the robot's planning to do. The robot can make sure it has all the information it needs, and then it can go on its way. You never want to hear or say, gee, I wonder why the robot just did that in one of these projects. So those are basically some of the guiding themes, and congratulate everyone in the room, and best of luck.
Hi, I'm Max Bajracharya. I'm here representing the JPL, UC Santa Barbara, and Caltech team. So if we go to the next slide. Here's an introduction to our team. JPL is leading the team, and we're focused on doing the perception and the world estimation, the manipulation, the mechanics and modeling, and the overall supervised autonomy. Caltech is responsible for the grasping and the whole body manipulation planning. And the locomotion area is being led by UCSB, and Katie Bill is actually here. Our perception lead, Jeremy, is here, and Nick Hudson, who's our manipulation lead, is also here. You've probably already met them. So next slide. Our technical approach is really building on many technologies that we've been developing under both DARPA and NASA and other agencies' funding. As part of the LS3 program, we're delivering near-field perception to enable Boston Dynamics to do near-field perception, obstacle avoidance, and footstep planning. We're also delivering a near-field pose estimation system for the autonomy. As part of the RMS program, we're developing object recognition capabilities that build on 3D voxel maps, and that also allows us to do closed-loop visual servoing and vision-based control, as well as some tactile sensing. In addition, as part of the RMS program, we've been developing, or Caltech, in combination, JPL and Caltech have been developing a multi-strategy approach to manipulation planning, as well as grasp planning, and then we combine that with a single-arm collision-free and dual-arm kinematically constrained motion planner that you see in the lower right. Underlying all of this technology is our own mechanics modeling infrastructure that allows us to do kinematics and dynamics both faster than real time for onboard systems, as well as at higher fidelity to do full and complete simulations of the system. Go on to the next slide. Our approach to walking is based on Katie's previous work on the L2 Learning Locomotion program, which focused on the Little Dog platform, and we're extending some of that work now into doing dynamic bipedal motion, locomotion. Our manipulation approach extends from our RMS techniques, where we've been developing a suite of controllers, and we combine these controllers into behaviors which we can then sequence and autonomously combine in order to do things like grasping of objects, actually controlling the trigger on the objects, force-controlled drilling, and investigation of the scene using tactile sensors, as well as force control and vision to do very fine precision manipulations, such as inserting a key or opening a door. And then finally, our operator interface grows out of work that we've been doing under NASA, where we control and sequence behaviors for the Mars rovers over significant time delay. So there we understand that you have to put together very long sequences to do days of operation. We're going to build on that, as well as some of our other tools, to be able to slide from very high-level supervisory control to shared control and direct control as necessary, and we're building on some of those tools in order to have that full sliding scale. So ultimately, we hope to be able to do very robust sliding scale and just supervised autonomy of the system.
Good afternoon. My name is Seth Teller. I'm the lead for MIT's Track B team. I want to introduce my co-investigators, Russ Tedrick, who is in the ECS and Aeronautics Astronautics Department and the Computer Science and Artificial Intelligence Lab at MIT. His expertise is in nonlinear planning and control, planning under uncertainty, dynamic bipedal walking. Also Julie Shaw. She is in Aeronautics Astronautics and in CSAIL. Her expertise in human machine systems, human-robot interaction, task planning and scheduling, and human factors. And Carl Yanyama from MECI, whose expertise is in autonomous and semi-autonomous control methods with an emphasis on vehicle systems. My own background is in ECS. I'm also in CSAIL, and I've had experience in things like geometric computing, spatial data structures, perception, HRI, mobile manipulation, and field robotics. So as we thought about tackling the challenge, we decided to leverage our collective expertise in a bunch of areas. One is in SLAM, in things like taking sensor data, fusing it into some representation of the surround of the agent, and doing eagle motion estimation, and perception, calibrating multiple sensors on different parts of the robot's body, analyzing terrain, finding objects and characterizing them, and so forth. I should mention here as well, we do have an automated calibration method that will take any number of LiDARs, stereo cameras, and IMUs placed anywhere on the robot and figure out where they are with respect to another. That's a publicly available source from our website, and I encourage people to try it if they're interested. Also, human-robot interaction. One of our projects involved a semi-autonomous 3-ton forklift that's shown there in the upper right that's commanded through speech and gesture. You can point to things in the environment, ask it to pick them up, transport them around, and replace them. It's currently being taken over by TARDEC. We have expertise in planning, legged locomotion, mobile manipulation of various kinds of robot bodies and task domains, including things like EOD and palletized supply handling that I just mentioned. Control and robustly executing complicated motions. Communication, which of course is going to be important here as we tackle this varying quality network link. And simulation and visualization. So we do a lot of real-time inspection of our algorithms, including logging and OpenGL visualization and so forth. This is using a tool called LCM that came out of MIT's 2006-07 DARPA Urban Challenge team. That is an open source tool. We urge people to check that out as well. It's fully interoperable with ROS. And finally, like everyone else, we're trying to do spiral design and implementing things end-to-end as we go. So if the key challenges of the DRC are dealing with noisy perception and imperfect dynamics, the way we're trying to address those in a nutshell is by integrating task-specific knowledge into the system, either prior knowledge or the operator's knowledge through a fluid human-robot interface. I'll stop there. Thanks very much.
Hello, my name is Ken Whitebread, and I'm here representing the Cooper team, as we call ourselves. I work at the Advanced Technology Laboratory at Lockheed Martin. As you can see, we also have on our team colleagues from Penn and from Rensselaer. From Penn, we have Professor Kostas Vanilidis and Professor Vijay Kumar, and their students and postdocs. And from Rensselaer, we have Professor Jeff Krinkle and his group working with us. Oh, I'm sorry, I didn't know this was animated. Just push it all the way through. Anyway. Most people started by talking about their approach, which I think is good, but I thought I would take a moment to talk about the problem again. A lot of these things in individual form have been mentioned before today, but nevertheless, to kind of summarize, why would you think about it the way we're thinking about the problem? You look at what you're being asked to do here for the robotic challenge and think to yourself, well, approaches that we know about don't scale very well. We have complex, eventually dynamic environments, high degree of freedom systems, and high dimensional planning that goes with those systems, and then the low bandwidth and latency problems with communications that Dr. Pratt especially emphasized for us this week. And on top of that, there's the problem of understanding the world, because we really are only doing this through the sensors and perception that are available on the robot. So the key idea, which was expressed, I think, well in the BAA and the concepts of the program, is to look to make the human not so much the disconnected operator, but a collaborator with the robot in solving the problem. And if you're going to do that, you have to give some thought to what is it humans can provide that robots can't provide, and the other way around. And we've kind of listed some ideas there about how that works. Humans really are the ones who can do not only the higher level sorts of cognition that we think about and that we know is not ready yet for prime time in any of our AI work, but also can think about what's going wrong when the robot is attempting to do something and it's not quite working, and can realize the difference between I have to stop and do everything over again, or I just have to correct this one small thing, and the robot will be able to do what I'm trying to get it to do. The robots, on the other hand, are very good at mapping environments and processing essential data and completing the actions that we need to do. Next slide. So, what is our idea for an approach to this? Well, it combines a lot of things, and I've kind of listed them here on the slide. But to kind of go around the horn here, we, like everyone else, are starting out with a technology baseline based on the work we've done and the work that our colleagues have done. And we're going to apply that and develop it further. For perception, we're going to use an approach that allows the human to interact with the robot and collaborate on the perception process itself, not just wait for the robot to get it right. We have various techniques in mind for whole body coordination that I've listed there, and in some ways more to the point, because we're looking for how to get the human in a position where he can make use of whatever it is the robot can do. We are spending a lot of effort on how we're going to have the human and the robot collaboration. It's going to be model driven. It's going to use the kind of predictive simulation that was mentioned by a few of the other teams, and again mentioned by Dr. Pratt, to allow the operator to do exploratory planning. And it's going to be based on what we call the shared world model that will be the basis for allowing the robot and the human to collaboratively build up an understanding of the world. We will also be doing a lot of regular testing and evaluation, and really trying to apply the kinds of processes adapted appropriately to a research project that a company like mine, Lockheed Martin, uses routinely with real-world systems. There's a lot to be learned in how to do difficult, complex research projects if you learn how to apply those things without getting in the way of the research. And I think that's my last slide. I think it counts in trying to finish the right number. So thank you very much.
Hello, I'm Jerry Pratt. I'm from the Institute for Human and Machine Cognition in Pensacola, Florida. Next slide, please. Our overall approach is trying to figure out how to make a real good user interface and a system that allows for collaborative problem solving between the human and the machine. If we click the next slide, I'll show a kind of example of what we mean by this with micro air vehicle system. This is a mixed reality display where a user can quickly model the robot. This is where model the world, and get the robot to do things that would have real trouble to do autonomously by exploiting human cognition and human perception. So here you can see a play forward view of what the robot's planning on doing. So the human has intuition into the planning system, and then once the human sees that, gee, that looks like a good plan, let's go ahead and execute it, then the robot does as expected. Next slide, please. So this is kind of what we're thinking for our interface. You have some sort of third-person view mixed in mixed reality, so that you have real data mixed with the 3D world model. So in the upper left, you can see a 3D world model, and upper right, you can see the model mixed with real camera image. And the key challenge is figuring out how you can answer the questions. What is the robot doing? What's it going to do next? Why is it doing that? How can it make it do something different by doing a good user interface? Next slide, please. We have a lot of experience in bipedal walking. If anybody's interested in some of our work, I can point you to some papers. Next slide, please. Here's some demonstrations. On the left, Atlas model walking while getting disturbed with falls. Middle robot is M2V2. Robot we've been working on that can do push recovery. And on the right is Atlas model walking up some pretty steep stairs, standing just on the stairs. We're developing a whole body algorithm that's momentum based so that we can do a lot of tasks that use both the upper body and the lower body at the same time, and are also now looking into multi-contact models so we can use our hands while pushing off the things. Next slide, please. We haven't done a lot of manipulation, so this was kind of the first mini challenge we set out for ourselves was, okay, let's forget about walking, let's just see if we can grab a box, lift it up, and so now we can move boxes from one table to another. And you can kind of see how our algorithm allows for control and stability while balancing, while also being able to manipulate things independently. Next slide. So here's some of our team practices. We do a lot of kind of extreme programming style practices. We believe that one of the biggest challenges in this project is going to be just managing software complexity. And so we do a lot of things where we're very obsessed with testing. We don't say any of our software is done until we have a test suite that proves that it's done. We do automatic builds, so anytime we have some new software, we check it in, it spies on the repository, checks it out, runs our test cases, and emails us if anything fails. I use a lot of agile planning techniques, pair programming, and a lot of visualization into our algorithms. Since most of the stuff is geometrically based, we try to have really good 3D visualization and see what our algorithms are doing. Next slide, please. We're going to take. We would like to take an approach that's fairly open. We do understand that this is highly competitive, but at least after each phase, we want to do under the hood meetings with other teams, and we know we can't do this whole thing ourselves. We're going to have to share some information and use some other open source software. Next slide, please. We have a pretty talented team, and so we're really looking forward to this project. Thank you very much.
Hello, my name is Hugo Guterman. I'm the leader of the Robotics team. The Robotics team is a consortium that includes three leading universities in Israel and 2 companies. There are a total of 20 PIs and 40 students in this effort. And actually we are very thankful for DARPA for bringing us such a challenge, because during the last 2 years we are looking for something that actually make us to work together. Now, the people that are here in this team came from different areas. We have experts from the area of perception. We have experts from the area of decision support system and decision making. We have people in the area of dexterity and so on. We feel that in order to success here, we don't want to write only papers. We actually want systems that work. And this is based on reality that we have experienced in several years. In Israel, we have systems that have been working in the area. For example, Israeli aerospace industry is a leader in the area of UAV and UCV. These machines have been saving people for many years. And they have the experience that can allow us to integrate all the technologies that we are developing here. Cognitive is a startup company that actually is in the area of artificial intelligence and has been working for many years in the ROS environment. Bar-Ilan University is in the area of decision making. Technion provides research in the area of dexterity, mobility, and perception. Finally, but not last, is my own university that have been the leader on the area of autonomous robotics for already 13 years, and where we have experience in air, ground, and sea. Based on this, we decided that actually we don't want more of the same. This challenge should be something that actually gave us the opportunity to create a real autonomous platform that is able to deal with the problem of not having communication. That is a real thing that exists in the field. For that reason, our approach is that we have people on the loop that can check if the situation is normal or not, can advise the decision making if it's okay to continue, or we need to change the strategy. But actually, what we want is that the robot continue to work. One of the things that please the second slide. The second slide, please. Okay. Our main objectives are actually create a system that allows adaptation, real-time adaptation of an environment that are changing. By experience, we know that it's impossible to create a system that will not fail. But if you create it with a different philosophy that actually you can adapt in the situation, then you can succeed. Perception is based on the same thing. How you deal with information, how you reduce this information, how you know where you are, even if you don't have all the accuracy that you need. In cognition, and this is I think an important point, we will be working on how to deal with uncertain situations, when we don't have enough information, when something cannot work as we expect, and how we can solve the situation in real time, without human intervention. Finally, we have been working a lot in the area of mobility, in robust locomotion over different terrains, and we want actually, we have a lot of experience on driving cars, and we really want to create a system that will be better than standard Israeli driver. Okay, this is a very high objective to have been in Israel. In any case, we are very excited to participate with you. We are open to share with you, and we hope to be in contact all the time with you. And good luck to everyone. Thank you.
Hi, I'm Chris Atkinson. This is the CMU Track B team. I'm very, very pleased to see Pittsburgh well represented. President Obama announced the National Robotics Initiative in Pittsburgh at Carnegie Mellon University, and now we see we have 3 Pittsburgh teams. I also have to confess that I screwed up. I got the email from DARPA, sent us the slides, I sent them the slides, and I realized I left off our webpage. So I whipped up a t-shirt, teamsteel.org, no spaces. Check it out. Got everything there. The other CMU team took the traditional CMU name, the Tartan stuff, so I had to do a Pittsburgh name. I do want to point out there's a Steelers game this weekend with the Redskins. So we have a lot to look forward to. Okay. 2 slides. What I tried to sell is that we have a lot of experience with a previous hydraulic humanoid built by Sarkos. You've actually seen good videos of it. And we also worked with the Little Dog program, DARPA Learning Locomotion, and the M3 programs. And I'll talk a little bit more about that on the next slide. Our magic bullets. We believe that the way the brain works and the way to do this contest is to fill your head with examples of behaviors. This is like the blockbuster theory of the brain. Whenever you need to do something, there's a phone call up to your head, and the little guy answers the phone, and you say, I need to turn the valve. He goes into the stacks, he finds the appropriate tape, he puts it on the tape player, he presses play, and you turn the valve. Okay? That's our ideology. We actually can improve on our stored behaviors by using fancy optimization algorithms with multiple models. Where is this library going to come from? It comes from 2 places. The first is we're going to, whenever possible, be human-like. We're going to actually have humans do the contest and capture their behavior using cameras and things like that. And we're going to do it over and over again with lots of different humans. And we hope we'll just cover the space, and that'll be enough. And our motto is WWHD. That's related to the motto WWJD, except in our case, it's what would a human do? Okay. When that fails, we're going to be robot-like. And what does that mean? We're going to be super logical, like Spock, and we're going to use optimization algorithms to figure out what to do. I'm very pleased there's a University of Washington team that's doing optimization. There's another team with an optimization expert, Strick from Germany. So we're going to have some competition on this optimization front. Let me turn the page. Okay, we've done some competitions before, and I can tell you what I think the fundamental problem is. The robot works in the lab, but then you take it out of the lab, or you try to get it to run on an identical setup, it doesn't work. The robustness of what we've done is typically very poor. So I think the fundamental research question that we're trying to address is, how can we generate robust behavior that works every time in every place and across all copies of the robot? And we think the answer, or the way to do this, is optimal control. Most people think that's a crazy idea because optimization sort of takes you to the sort of limits where things are very brittle, not very robust. So the intellectual research question is, can we make it work and use optimal control to generate behavior? Okay, that's it.